So why important? What's the big deal with predicting states of matter? Well, I see two issues. One is you could be a Coca-Cola factory in Alaska. Maybe it's really cheap there, but the water's good, right? Get the glacier water or something, I don't know. But you're a Coca-Cola factory in Alaska and it gets cold. You want to know at what pressure, because you're pushing the stuff through, right? What pressure does it turn into a solid? What pressure, what temperature do you need to keep it above to keep this a gas? Because you're not talking about changing compounds, you're just changing states. So all it is pressure and temperature, and you mess with either one of those, you can change states. You can keep it at this perfect temperature and change the pressure, it's going to change states on you. You can't stop it from happening. Keep the pressure the same, change temperatures, which is more common, right? In the cooking and stuff. Keep the pressure the same, change temperatures, it changes states. So being able to predict that, not only be able to predict it, but be able to know how much energy it takes for that to happen. It really helps. So the common phases of matter, what are they? Jarixa? What are the phases of matter? They were what again? Solid, liquid, and gas. Are they all at the same energy? Vivian, are they all at the same energy? Are they all at the same energy, Vivian? Solid. So it's all the same compound. So you have ice, you have liquid water, and you have water vapor. Are they all at the same energy? They could all be at the same temperature. You could keep them all at the same temperature. But all those different states. What's the difference? How do you picture solid? How do you picture liquid? How do you picture a gas?
Molecules are bunched up in a solid.
And they can't even move, right? They're immobilized in a solid. In a liquid, now what? Yeah, they kind of flow around each other, but they're still stuck, right? Gas. They're flying around the place. So which one would have the most energy? Gas, right? It's moving around the fastest. So it's odd to say it's all the same compound, all the same temperature, but it's a gas, it's a higher energy state. It's kind of like it's a ball, but it's just at a different height. It has more energy than the ball down here. It just has more energy. So gas has more energy than a liquid, which has more energy than a solid. So they kind of go up in that sense. It sounds odd, even though they're all at the same temperature, but it's true. What are the common phase transitions? Can you name a phase transition, Crystal Munoz? Phase transition, going from solid to liquid, liquid to gas. What do they call these guys? What's one of them?
One's vaporization.
Okay, vaporization. We never use that in common layman terms, but fine. She wants to do vaporization. Okay, vaporization is going from what state to what state, Gabby? Liquid to gas. Okay. Is that absorbing energy or giving energy off? Crystal Zamora. Going from liquid to gas. Is that it's raising. It's absorbing energy. Right. You have to go from here to there. That's absorbing energy. Liquid to gas. Vaporization. So is that endo or exothermic? It's absorbing, so it's endo. Vaporization. It's absorbing, so it's endo. Danny, how about another phase transition? Melting. Okay, melting. Erica, melting is going from what state to what state? Melting. Solid to liquid. So solid to liquid, Jasmine. Endo or exo? She said melting. So is melting endo or exo? Endothermic. Good. Another phase transition, Sabina. Another phase transition that we haven't mentioned yet. Freezing. Okay. Would freezing be endo or exo, Allison? Freezing will be exo? We're going from what state to what state? Liquid to solid. So we're going, see, do you see what she's saying? You're going down the energy ladder. You're going to lose heat. So what do we say? Freezing? That's an exothermic process. Tegan, how about condensation? Condensation, would that be endothermic or exothermic? And exo? Does it make sense for it to be exothermic? You're sitting there at the picnic table, right? You pull out the cold brewski, right? And then it starts condensing, right? You get all this liquids collecting around on the outside. Is that thing getting warmer or is it getting colder? It's getting warmer. Why is it getting warmer? Because condensation is exothermic. It's giving off all this heat, right? Condensation. You think, let's, one more, Jerixa. You think of one more? One more phase transition? Ooh, evaporization, good. So is evaporation, Danny, endo or exo? Evaporation. Going from, she says endo, right? Going from liquid to gas. Evaporation. Same as boiling, right? Okay. The book doesn't give us equations for this type of problem, so we just have to analyze it. And I don't like to memorize anything, so I like logic. It works every single time if you use logic. So Vivian, not even reading this question, they want to know how much heat. What are the units of my answer? If my answer is heat, kilojoules. And I'm glad she picked kilojoules because maybe she scanned through here and she saw it. She didn't say joules, she didn't say calories, which would work, but kilojoules are going to be the most convenient answer. Bless you. Kilojoules are going to be my answer. Okay? So I want to boil 20 grams of water. Now this water's at 50, here's some water. Assume it's at 50 degrees Celsius, which is kind of pretty hot. It's pretty warm, 50 degrees Celsius is. Is it going to boil at 50? No. You have to heat it up to what first? 100 degrees. Is that going to take heat? It's going to, yeah, that's going to be positive heat too, right? So my heat is going to be the heat to get to 100 degrees Celsius. Okay. I'm finally at 100 degrees Celsius. Now I can boil. Does that take energy? Yeah, it does, right? We just said it did. It took, you're going from a liquid to a gas, so it's going to take more energy. So again, plus. Now the heat to, I guess you could call it to boil, but I kind of like the idea of just saying H2O liquid to H2O gas. That you need that reaction to happen, and that's an endothermic reaction. It takes energy for it to happen. Okay, so we're going to get so many kilojoules for this one. We're going to get so many kilojoules for this one, and then we'll get our answer. Okay, let's see how we get those two parts now. The first one. Okay, the first one. Our heat is going to equal. Now, they gave us some information here. Which one of these are we going to use to get this first part, the heat needed to warm up the water? Which one of these do you think it's going to be? The heat needed to get the water up to 100 degrees Celsius. Heat capacity. The reason why I like heat capacity is because it's got this darn temperature in it, right? That's the energy it's going to take to warm it up 1 degree, 2 degrees, 3 degrees, whatever. We're going to need this. So the question now becomes, since we don't have an equation, we don't know whether we should flip this or just write it as is. But if you look at it, you know. Why would you leave it as is? Because it already has the kj on top. And you know you have to add kj plus kj. So that means leave it alone. Don't flip it. There's nothing wrong with flipping it, but in this case, it would be wrong because kj would be on the bottom. You can't add 1 over kj. So we're going to write it exactly as it's written, 0.075 kj. And don't write dash. Write it this way. It's so much easier to see what's going on. Mole degrees Celsius. Okay. We need to multiply this by 2 things to get, so we have just kj. We need to multiply it by what and what, Crystal Munoz? Need to multiply it by the, well, what's this? This guy. Yeah, we don't know how many. We're going to have to multiply it by moles. Otherwise, they're not going to cancel. We got to get rid of it. So we got to get a number for moles. We have to get a number for what, too, everybody? It's degrees Celsius. Right? So they'll cancel. Now, what numbers do we put in here? Okay, the moles part first.
Will we convert that to?
Perfect. Convert the 20 grams to moles. 20 grams. Okay. And we use, what's the technical word to convert grams to moles? It's mole bridge is a reaction.
Oh,
Stoichiometry is a fancy way of saying mole bridge. Molar mass. Use molar mass, right? And the molar mass of water, 2 hydrogens plus an oxygen, you get about 18. Those 18 grams have to go on the top or bottom. Bottom, so the grams cancel. And it's always, always 1 mole on top. So 20 divided by 18. I shouldn't have shut the lights off. 1.1 or so? Thanks. 1.1. So that's 1.1 moles of H2O. That's what we'll put in for the moles. Now, how many degrees Celsius do we put in?
50, right?
How do you know it's 50?
I don't know.
You should do final minus initial. And that's why I got to change this question from 50 and make it 25 or something. It'll make more sense. Because if it's 25, then you're going to put in 75 here. Because it's the degrees that you got heated up. It's the change in temperature. So 100 minus 50 is 50. So it's a bad, poorly written question. I'm going to change that for next time. But it's 100, final minus initial. Okay. Now let's add on the other number of kilojoules. We have to get the heat necessary to convert all that liquid water to gaseous water. And now we're going to use this other term right here. Gabby, should I leave that term alone or should I flip it? This guy right here. Leave it alone. Why? Because kj's on top. And you know you have to add them up. So, and don't do the slash thing. Make that obvious, what's on top and what's on bottom. That's why we did that whole box thing. So it's obvious what's on top, what's on bottom. We have to get rid of the moles, Crystal Zamora. How do we do that?
So, is it the same thing with the water?
Yeah, because the exact 1.1 moles. It's the exact same amount of water that we're going to boil. We want to boil all of it, so it'll be 1.1 moles again. Okay. Add them up against kilojoules. Now, before you do this on the calculator, let me give you some friendly advice here. Life is much less frustrating if you trust that calculator, right? Don't write anything down. You're going to take 0.07, look, recognize what's on top and what's on bottom. All these are on top. So 0.075 times 1.1 times 50. You can hit equals if you want, equals, plus 46 times 1.1, hit equals, one answer, nothing written down. Odds are you're going to, if you keep doing that and make it a good habit, your life in this class is much less frustrating. So if you do that, you should get about 54.7. Okay. Nothing's written down.
Kilojoules.
Yep.
We-
Except everything else canceled out.
Kilojoules of water. Just that?
Just heat. Just kilojoules.
Oh,
Because kilojoules is heat. Okay. So that's pretty much how we have to handle these problems that involve how much heat does it take to warm up this substance or to boil this, or to, you have to get things to their freezing point or to their melting point or to their boiling point, and then you convert states. So very often there are 2 kilojoules you have to add up. Yep.
Why did you put temperature side?
For this one, because all he has is kilojoules and moles. There's no Celsius to cancel. It's a good question. See that? There's no degrees Celsius here. It's not there. So we didn't do anything with temperature. We only wanted to get rid of those moles. So in that sense, I was just trying to use logic. Logic dictates only moles. So the phase diagram of water. Okay, you want to be able to draw this phase diagram of water. And all phase diagrams of anything, all they are is pick a pressure and pick a temperature, and it will tell you what the state is, solid, liquid, or gas. That's all a phase diagram is of any compound. You pick any pressure, pick any temperature, you look at the phase diagram, and it tells you, oh, that's going to be a solid. Oh, that's going to be a liquid. Oh, that's going to be a gas. So we should know the phase diagram of water. So this is what it looks like. So we need a plot of pressure and temperature. Okay? So all the pressure's increasing as you go up, temperature's increasing as you go to the right. And let's show you what it looks like here. You have one curve that goes like this, with a dot on the end, and another one that goes back. And where these lines intersect, you draw another dot. Okay? So these 2 dots are the 2 points that you need to name on all these phase diagrams. So where they interconnect is the triple point. And then the other point where it stops is called the critical point. And we'll mention what the significance is in a little bit. Okay, let's see if we can figure out where the solid, liquid, and gas are. I don't know if you can see, but there are 3 sections here. If you imagine being way out, way out here somewhere, the temperature is extremely high. The pressure is really low. What state would that more than likely be? Solid, liquid, or gas? Gas. Temperature is really high. The pressure's low, so the pressure isn't going to compress and force this stuff into a liquid or anything. The pressure is really low. The temperature is extremely high. Things are moving around really fast. Gas. Let's look at this one, this state right here. The pressure is extremely high. Go way, way up to the top here. The pressure is extremely high. The temperature is really low. That whole thing must be solid. That means the middle one must be liquid. So how does this work? You pretty much just, I don't know, you pick this pressure, whatever it is. Pick this temperature, whatever it is. You see where they intersect? Oh, I'm a solid at that pressure and that temperature. That's all it is. Okay? So I shouldn't have done that. Okay. So this triple point, what the triple point is where you have solid, liquid, and gas all coexisting at the same time. So it's pretty easy to do. Just take some liquid water, dump some ice in there, and let it equilibrate. So that means all that ice can't disappear on you. You got to have some ice in there, and it's all equilibrated. You've left it there for a long time, and there's ice and liquid in there. Put a thermometer in there. Doesn't matter where you're at on the planet or what planet you're on, space station, wherever, it's always going to read the same temperature for if you have the same compound in there. So it's just a property of that compound, the triple point. Kind of neat. So you can use it to, if you have two thermometers, if they just make a solution of water with ice, and you can calibrate both thermometers, you're going to measure exactly the same. So it's kind of neat. Critical point is a little more complicated. They never do this, but I like drawing it. I like drawing a dashed line. Because if you go beyond that dashed line, if you go on this side of that dashed line, all right, because this is it would come down to this T. If you increase the temperature above that red T, you cross the border. Man, things are now moving so fast, the pressure doesn't matter. They're moving so fast, you can't get a liquid anymore. It's impossible. You can crank the pressure up as high as you want, and you're not going to get a liquid. It's going to stay a gas. But it's not the typical kind of gas you're used to thinking. It's too dense to be a gas. It's a whole new state. Supercritical fluid. No. It's something that's not dense enough to be a liquid, too dense to be a gas. It's a totally new state. And I mention it because, well, it's there, but I also mention it because I really like coffee. However, I'm getting old. So that means no more caffeine. So I drink decaffeinated coffee, right? But us coffee drinkers who have been drinking coffee forever want that decaf coffee to taste right. How the heck, now when you take organic, you have a better feel for this, but how do you get an organic compound like caffeine out of the coffee bean and leave everything else there? Because you can't be messing with my coffee bean. I want it all there, just the caffeine gone. If you take carbon dioxide on its phase diagram, crank up the temperature, have the right temperature and pressure so that carbon dioxide is now a supercritical fluid. All of its states, it's whole different properties, whole different world. I don't know who figured this out, but they are extremely, extremely rich. Because supercritical fluid carbon dioxide dissolves caffeine. Awesome. So it dissolves, put your coffee beans in there. The only thing it dissolves out of there is the caffeine. And then you just warm it up a little bit, or cool it down in this case, cool it down. Now you have regular carbon dioxide again. You can use the same gas, decaffeinate some more beans, make it a supercritical fluid, decaffeinate the beans, get your carbon dioxide back, just keep doing it. And you make a buku dollars. That's super cheap. So supercritical fluid is just a whole other state that people play around with. Okay. Vapor pressure curve. So this is your phase diagram for water. Okay. And I think no matter what phase diagram you draw, they say draw a phase diagram, you're going to draw this. You draw the lines and label the triple point, critical point, label solid, liquid, gas. And it's just the numbers that are going to change. But one other thing. This line right here. Water is the only compound known to man where it's bending backwards. So only when they say draw the phase diagram of water, you can have that line bending towards the p-axis. Everything else is bending the other way. Now, why is this a big deal? Without that, there wouldn't be any life if you follow the theory of evolution. What do they say? I don't know. Didn't they say the little fishies flopped out of the oceans or whatever, and then that's Life started in the oceans. Isn't that the big? You guys are the biologists. Isn't that what they say? Well, take your evolution class. You'll find that out, right? So the argument is life started in the ocean. So if you're in Minnesota, at the lake, Alaska, wherever, it's getting to be October. It's getting cold. The lakes are starting to freeze, right? So these little ice crystals are starting to form. Where's it coldest? At the bottom or the top of a lake? The top has all the sunshine shining on it and stuff. Right? It's a lot darker down there, right? So it should be a lot colder on the bottom. Go swimming in a lake and you find that out really quick. But yeah, it's colder on the bottom. So the little ice crystal forms. Does the little ice crystal float to the top or does it float to the bottom? Ice floats to the top because ice, solid, is more dense or less dense than liquid. It is less dense. That's the only compound known to man where that happens. Everything else, the solid is more dense. It sinks when it freezes. Water, no. Water's special. Ice rises. Why is that a big deal? Because it freezes at the top. You still have liquid water on the bottom. Imagine if it was the other way around. If ice actually sunk, the whole damn lake would freeze because it would freeze from the bottom up. Oceans would have frozen. Life would have been impossible according to all the theories that we have. There's a lot of little things about this planet like that you start, I guess it irks me when I hear the argument, there has to be life out there because look at all the possibilities. Look how rare life is here. Water's a good example. Another example is our moon. You don't know this unless you take the classes or you do a lot of reading, right? And with our moon, it's huge. It's way too big for the size of our planet. But what good is it? Mars doesn't have one. And you saw the little rover pictures. Yeah, it's cold there, but come on. Life could have happened there, but it didn't. Why? Because the argument is that the North Pole was here on Mars. Now it's over here. Then it's over here. Then it's over here. Remember, geological time, 1,000,000 years is nothing, right? So it's just they're moving. The poles are moving all over the place. It's never stable. The orbit isn't stable. It doesn't have a big honking moon. We do. Our North Pole stays there. It might shift around a little bit, but not much. South Pole stays, right? Geologically, it doesn't. And there's several things like that, I think, that are, anyway, I kind of went off track. But, okay, we talked about vapor pressure curve is what we're supposed to be talking about. Vapor pressure curve is right here. Oh, one more, just to remind you again. So any phase diagram, it's only water where that pressure liquid curve is going back. Otherwise, they're always going forward, right? Because the density of the solid is more than the density of the liquid. Vapor pressure curve, where is it? It's right here. Here's your vapor pressure curve. If you want to know what temperature things boil at, change the pressure. You change the, I don't know, like pick this pressure. It will boil. You have to go to the vapor pressure curve, the curve that's between the liquid and the gas. And you can see what temperature it boils at, right here. If you crank up the pressure, it now boils at a higher or a lower temperature. Right? Crank up the pressure, it now boils at a higher temperature. Crank up the pressure even more, right? It just keeps getting higher and higher temperature. Okay? So you crank up the pressure, the boiling point changes. It boils at a higher temperature. Okay? So boiling really occurs, this is more information than you need to know, but I think it's interesting. Boiling occurs when the vapor pressure equals atmospheric pressure. So what is vapor pressure? If you fill a container like this with water, okay, and I cap it, and I let it set for a long time, there's pressure in here. It's atmospheric pressure. you're living in atmospheric pressure. I mean, how much is atmospheric pressure? It's like 15 pounds for every square inch. All it is just the weight of all the air above you. It's about 15 pounds per square inch. So there's atmospheric pressure in here. Why don't you feel, that's a lot, right? 15 pounds per square inch. You're drowning and you have drowned in air. That 15 pounds per square inch is inside you. You don't feel jack, right? You're equilibrated with it. It's inside you. So that 15 pounds per square inch is also in here. And that pressure is made up of all the gases that are there. So what gases are in air? You've got, what gases that are in air? Jasmine, what's in air? Oxygen, you'd be dead without it. But that's only like 20%. 70-some percent it's mostly nitrogen, right? But in this case, we also have some water, okay? So the atmospheric pressure is, going to be around 15 pounds per square inch, 14.7 at sea level. But part of that pressure is due to water in this case. So it's like 0.01 pounds per square inch or whatever is water. But if I heat it up, right, heat this guy up, cap it, and let it equilibrate. So I have really hot water in here. I'll have more water vapor in here. The vapor pressure went up. It's not boiling yet. I just heated it up. But now there's more pressure in here due to water. Heat it up. Keep heating it up until that pressure due to water is the same as atmospheric, what's pushing down on it. Then the thing boils. So, and it doesn't matter how much water you have. This amount or that amount. Water only boils when when vapor pressure reaches atmospheric pressure. You heat it up, vapor pressure increases until it boils. So that's why boiling point doesn't change. It doesn't matter how much water you have. It's all going to boil at the same temperature. You just have to change the pressure. That's the only way to change it. Now, for example, you're a pastaroni manufacturer. You guys never read these things, but when you start living on your own, you get bored and you start reading all these things, right? And every single box has an at high altitude special direction, right? And why? Those poor guys in Aspen. Ooh, yeah, they're so poor, right? But they do have to follow the special directions. Why? Why are there special directions for these special people? Because what? Their atmospheric pressure is different. Is it higher or lower? They're up in they live in the clouds pretty much. Is there more or less air above them? There's less air above them, so atmospheric pressure is going to be less. Right? Atmospheric pressure is less. So if atmospheric pressure is less, their water is going to boil at a colder or a hotter temperature? Colder. Look at the phase diagram, right? So our water at sea level, it boils really close to 100. We're like 99.5 degrees Celsius. Their water might be around 91 or 92 degrees Celsius. It's still hot. It'll scald you, but it's 91 degrees Celsius. Those little noodles aren't going to cook as well at 91 as they will at 99, our temperature, 99.5. So they change the directions a little bit. And they say, okay, in this case, they're changing the water. In other cases, they might have you add a little bit of salt, but that's not a very good change. People think sodium's bad, right? So they try not to do that one. But they make some little changes so that the rest of the directions will work. Okay. Let's see. Here's I think I covered everything. Oh, I didn't talk about this one. Let me show you this one. I don't remember if did I show you this? No. Okay. So we're talking about atmospheric pressure, right? So you get a degree in some science field, and then these little elementary schools ask you to be a science fair judge, and it's so much fun, right? So you go there, and all these little kids are lined up in the hallway in the library or someplace, and usually their parents are there, and they're all excited, and So there's this little girl, and this is what she had. She had a ruler, newspaper, and a hammer sitting there, and she was holding the hammer pretty eagerly, and none of the science fair judges were walking up to her. No poster, no nothing. This is all she had. And this is like this is like 4th grade. So it's my job, right? So I should go see what the little girl has here. So what's your project? And she wouldn't tell me at all. She wanted me to do the experiment. So I said, fine. So she explained in detail, and of course I didn't do everything right until she had it just the way she wanted. So this paper had to be lined up just on the edge, and the ruler had to be underneath here, right? And that's about it. Something like this. And then she gave me the hammer, and she said, hit the ruler as hard as you can. I mean, there's people all over the place in here, right? So I'm kind of careful. It kind of pushed some people out of the way, because everything's going to go flying. It should go that way, right, towards Sabina, right? So, but I was too scared at first, so I hit it soft. But once I hit it soft, I think I already tore this, but it should be okay. Once I hit it soft, I recognized what was going on. And I don't know if you can see it. I should get a different one, because I messed that one up. I think I have another one in here. Here's another one. Use this one. Okay. So when I hit it soft, I don't know if you can see what happened, but what happens to that newspaper, right? It sucks around the ruler, right? So when I hit it soft, I felt so confident. I thought, oh, okay, this is going to work. I understood it. Well, how many pounds were every square inch of atmospheric pressure? Around 15. Look at all these square inches here. In just one column alone, I've got to have like 200-300 pounds. This whole thing has to be, I don't know, I would say close to 1,000, 2,000 pounds of atmospheric pressure. That's like sticking this under a car and trying to lift the car with a wood ruler. It's going to snap like a twig, right? There's no way you can do it. As long as you don't let the air, the atmospheric pressure, get underneath here. You have to do it fast. You do it slow, yeah. Everything's just like you are. It's drowned in air. But if you do it fast, oh no. That you're not giving time for the atmospheric pressure to get underneath the newspaper. Oh, it broke again. Oh. Man, these are tough rulers. Let me try it over here. All right. Maybe I didn't. I need a flat paper. Let's try it again. I gotta do it faster and harder here. I know. I should have you do it, Tegan. There it goes. Well. See, the paper's okay, but these rulers are bad for this. But see, it broke it. But there's a wired doohickey or something in here. But right? You just have to do it fast. So atmospheric pressure is there. She win? No. I don't really do that part. I think that the problem is with me as a science fair judge, because afterwards, I asked her, why does this work and stuff, and she was so far off, right? And I can't just shut up. I have to explain to her, just exactly what was going on here. So I wasn't mean or anything. She wasn't crying. No, it was a good conversation. So when I left, she understood why this worked, right? How people see things. They Google. They Google this stuff, right? But one dude, if I am ever at a science fair, one dude that is never, ever, 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 ever going to win is whose project? If you've ever done the science fair project, this is the one that always wins. Starts with the V. The dang volcano. Wins no way. You know why? I'll tell you why. My son was in 3rd grade. So, science fair. Woohoo! Right? So, his science fair project was, here, I can show you. This is a science fair project. What can stop a radio wave? So he put this radio everywhere, inside plastic bags, underwater, buried it. He put it in drawers, all over the place. And he was getting really frustrated. He could not find anything that would block a radio wave. So I gave him some suggestions, and this is, I get it to come in. This is one of them. I need to find a better station than that. That's coming in good. It was. Okay. And it's not coming. There it goes. All right. So you can hear it. You can hear it. Hear the radio. Right? What if you punch a bunch of holes in there with your pencil there? Oh. Yeah, a lot. A lot. Okay, how about now? Right? So, metal blocks radio waves. Metal does. As long as the hole is smaller than the radio wave. How big is a radio wave? This. I need a hole this big. So there's no way it's going to block radio waves. You can put your cell phone in here. However, to block a cell phone, what region of electromagnetic spectrum does your cell phone operate on? It's not the radio waves that are nice and safe. They don't interact with your body. You are a bag of water. Microwaves interact with water. And you know they do because you have a microwave oven. Cell phones are on microwave. They're a lot smaller. Look at your microwave oven, the metal screen in the front has those little holes. Microwaves are just a little bit bigger, about a centimeter. Okay. But anyway, cool science fair project, right? Who won? The volcano. Oh, and he got, and then I went ahead, I was so mad, I didn't say anything to them. I submitted it to an international journal of chemical education. Extremely competitive. Did it get published? Yes. An 8-year-old got published in the Journal of Chemical Education. Right? Oh, I was ready to submit it, just send it to the principal and everybody. But the thing is the science fair judges didn't understand it. They thought it was a trick. That's the only thing I can.
Oh, that makes sense.
That's the only thing I can figure. So they're not going to let a trick win, but they'll let the volcano win. Stupid. Okay, we'll do this one and then we'll call it a day. All these problems are really pretty much the same. So don't feel guilty when we don't get through all these because they're all just the same thing over and over again. It's good practice. So we are going to draw a phase diagram of bromine. And here's all the information that we need is right here. So go ahead and draw the phase diagram. You need the components. You need pressure, you need temperature, and you draw your lines. Okay? Now there's only that one bar between the solid and liquid, right? Which direction should it go? Should it bend towards the p-axis or away from it? Away, because it's not water. It should bend. I got to erase the liquid now. It should bend away. And you can either just look and say, oh, it's not water, or look at the densities. The solid is 3.4. The liquid is 3.1. Yeah, so it's the opposite of water. Okay, so there's our 3. And label everything that's important. Well, I guess you should write triple point and critical point. And label the solid, liquid, gas, that sort of thing. Okay. And then, oh, they want numbers. Triple point is at negative 7.3 temperature-wise. So that means this is negative 7.3, and the pressure was 44. And then they had the critical is 315, and the pressure is 102. Okay? So that's pretty much all you are expected to write for the first part. So any question on why I did what I did? Okay. Let's answer the first question. I want to fix this. I want this to be written more inside. Because remember, above that dashed line, a liquid can't exist. But they never write in the dashed line. I like the dashed line, but a lot of people don't draw it. Books don't draw it. Yep.
So you said, what was the supercritical fluid?
Supercritical, they never write it. All we're interested in is solid, liquid, gas. That was more information than you needed.
Right. Where does it exist?
It exists where since they don't like to name it, that's probably why they don't draw in the dashed line. You find the critical point and just draw a line above it. So that means liquid is all this way, supercritical fluid is all on that side. But all we're interested in is solid, liquid, gas. Okay, so you're at this first question. You're a bromine vapor, so that means you have to be a solid, liquid, or gas. If you're a bromine vapor,
Yeah.
you have to be a gas. So you're somewhere over here, right? But not just somewhere, it's 40 millimeters of mercury. So I guess you're somewhere down here, right? You're somewhere on this dashed line on this side. Right? Because you have to be at 40 millimeters of mercury. That means you're below the 44, but you have to be in the gas. You're somewhere on this dashed line. They didn't tell us what the temperature is. Okay. So when cooled sufficiently, let's just pretend I'm right here. I'm going to cool. So do I go to the right or to the left if I'm cooling? Go to the left. So I'm a gas. I'm going to condense to a solid when I cooled sufficiently. Very useful type of information. You could be that Coca-Cola plant. It's really cold out there. If you get it colder and colder and colder, you might go from a gas to a solid. All your valves, everything gets clogged. The phase diagram would tell you this information and forewarn you. Bromine vapor at 400 millimeters of mercury. That's way the heck up here somewhere. Just pretend that's 400. And I'm a vapor, so I got to be over here somewhere. Okay. Bromine vapor 400 condenses to the liquid, right? Because after you have vapor and it condenses into a liquid. Okay. So that's all the game you're really playing. Phase diagram is pretty much just give me a pressure, give me a temperature, and I'll tell you whether it's a solid or liquid. And it also tells you what temperature things boil at with different pressures. That's pretty much all it's used for. So, yes, Gabby. Oh, because of the density story. The density of the solid is bigger than the density of the liquid, the opposite of water. So that's why it's bent the other way in comparison to water. So have a good day.